One of the very weird things that can happen with rational functions is that a rational function can have a hole in it. And this is important for us to understand as human beings doing mathematics, because this is something that a lot of machines and programs don't really understand. So for example, the graph of the function that's described on the screen is actually shown on the right. So this function, which is clearly a rational function, has this graph. And of course that looks like just a completely straight line. So it's the first time we've seen anything that looked like a rational function having a graph that looked anything like that. So it's a little bit perplexing at first. But there is definitely something going on here, because you would not be able to evaluate this function, for example, at -4. If x was -4, if you try to plug -4 in for x, you're going to get something in the numerator divided by 0. And so that's going to be an error message telling you that that's a bad value. But on the graph, it looks like there's a point here. When the x-coordinate's -4, it looks like there's a perfectly good point there. And that's because Desmos does not have the ability to pick up on the fact that of all the points that are on this curve, the only one that's not really there is this guy right here. So this graph has a hole in it. Meaning that the function is undefined there, but we don't have asymptotic behavior. It's not undefined, and we have the asymptotes going up and down. It's undefined, and the function just sort of takes a little hiccup as it goes past there. So there really is no point on the graph that's right there, but Desmos doesn't know that. Desmos just randomly picks a few points and goes, oh, it's straight, and just draws it in. So the challenge for us is figuring out how to figure out that y-coordinate. Now we can get a pretty good guess here by just trying to estimate from our graph about what the y-coordinate of that hole would be. But let me just show you a way that we can use the mathematics that we know from algebra to actually say exactly where that hole is. So to do that, I'm going to first put my graph away, and maybe I'll just set it up here for the time being so we can come back to it. Okay, so the reason that we have a hole here, even though we learned that when the denominator was 0 we should see an asymptote, is because of a subtle thing in our flowchart for analyzing these things. We said that when we have a rational function, that we're going to get an asymptote any place where the denominator is 0 but the numerator isn't. And so that's really the key here. The issue is when x is -4, not only is the denominator 0, but also the numerator is 0 when x is -4. And that's why that looks different than the cases we've analyzed before. And so what that means is that the numerator, 5x squared plus 17x minus 12, must have x plus 4 as a factor. And so to see the connection, I would need to factor this numerator. But I'm not just factoring it from scratch. I know that one of the factors has to be x plus 4. And so I can just go through thinking about FOIL. For example, I know that the first term here should be 5x because I know that f5x times x is 5x squared, and that's what my polynomial starts with. So I know that should be a 5x. And similarly, this thing ends with minus 12, and this is 4. So in order for the last two things to multiply together to be minus 12, I would need that to be -3. And it's worth taking just a second to check, but the outer here is -3x, and the inner is 20x. So if you add up the outer and the inner, you do get 17x. So we have to factor this, but we're cheating because we know that that x plus 4 must be a factor. It must share a factor with the denominator in order to have that behavior. And so that means that our f of x could be rewritten this way. And now I'm in a situation where I see a common factor in the numerator and the denominator. And in particular, the x plus 4 that's in the denominator is a factor of the numerator. And so we can see that the function, if I made up a new name for a function, the function 5x minus 3 is identical to this. These two things are exactly the same thing because I got the bottom one by canceling something in the first one. They're not exactly the same. They're always the same, except at -4. And the reason I say except at -4 is because the original function was undefined at -4. When we tried to plug -4 in, we got an error message because it had division by 0. The second function, this g of x function, does not have any problem at -4. So I could just plug -4 in here. What I'm calling g at -4 would be 5 times -4 minus 3 equal -23. So the g graph that's identical to the f graph everywhere except at -4 has its y-coordinate at -23. So this g line goes through -4, -23, and that's identical to the f graph except at that one point. And so this is going to be the answer to my question. The hole in f is just exactly that point that's on the line. And if I go back to my Desmos graph, you'll see that that is in fact consistent with what we're seeing on the graph here. The equation, I'll just write it down again. So the equation g of x equals 5x minus 3 is the equation of that line. We know other ways to figure out equations of lines, but we could verify that's what that is. And so the point right here has coordinates -4, -23. So those are the coordinates of the hole in the graph of f.